Our next set of talks, we are going to start exploring metacognition as it relates to reasoning about machine learning systems. And we'll start off with my colleague, Huawei, who's a new faculty member here at ASU.
Right. Thanks, everyone, for coming. And my name is Huawei. I'm currently an assistant professor at ASU in the School of Computing and AI. Today, I'm going to talk about sharing some of our recent work on trustworthy decision-making in the real world through uncertainty reasoning. So here is my research question for me and my lab. We want to answer this question, say, to what degree can autonomous agents make trustworthy decisions in real-time dynamic domains in the presence of real-world data? So with this highlighted keyword, you would see like we do a lot of work in data mining because we're dealing with the real-world data, especially the spatial temporal data mining and urban computing with the applications in the urban domain. And since we're doing like real-time dynamic domains, we do a lot of like multi-agent systems and multi-agent modeling. And those are some of the simulators we built. This one is one of the, in China, it's one of the top playing games. Is sort of like the League of the Legends. You, as a player, you control the agent here through your button, and you compete with each other. It's a multiplayer online battle game. And this one is used to test the generalization ability of reinforcement learning agents on coping with different enemies. And we also build simulators on this one. This one is called an epidemic simulator. We simulate how the coronavirus spread on the space. And each point here is a human, and different colors indicate whether they are infected or not. And we also mostly working on the urban domain. We also build the traffic simulators. Here, where we mimic the movement of vehicles and how they are influenced by the traffic signals. So you can see that most of the works we're doing is doing simulation, and based on this simulation, we're trying to judge to what degree the autonomous agent can make trustworthy decisions. In order to make trustworthy decisions, one of the key techniques we use is machine learning, specifically reinforcement learning. I hope you guys all know what reinforcement learning is. It's basically learning to act in the environment through trial and error. And speaking of the decision-making in the real world, there are currently 3 aspects of models. The first one is the descriptive analytics. Say, in autonomous driving vehicles, one of the key descriptive analytics model is to say, given you an image, I try to detect what is in the object. I try to describe what happened in the past. And the second kind of model is the predictive analytics, where we try to predict what will happen in the future. So given you the trajectory of an object, we try to predict what will happen in the future, like how this object is going to move. And those two kind of models, predictive and descriptive, they are also requiring some human input before they are actually transforming into certain decisions. Say, with this objective detection or this trajectory prediction, we still need human input to decide how do we steering our car, right? And similarly, in other tasks, say, given you certain data, you try to impute the data to recover the whole data in the past, or given you some demand in the past, like how many passengers in the past, and then you're going to predict how many passengers there will be in the future. So these two kind of models are pretty well studied in the past. And speaking of the decision-making, what we are doing is we try to focus on the third kind of task, is we try to get rid of this human input to get a more automated decision-making process, where the goal of this prescriptive analytics is try to answer the question of how can we do to make things happen. And this one is widely believed to be with more difficulty and more valuable. So if you ask a neuroscientist, or if you ask a Christian, he might say, we have our human brain for one reason and one reason only, that is to produce adaptable and complex movement. And those movements are the only way that you have to affect the world around you. And this movement is what we see for those predictive analytics, the output for this analytics, right? And one classical task in the decision making in the real world would be, say, for autonomous driving vehicles, the decision would be how do we steering our car, or how do we control the traffic so that everyone can move faster in the city, right? So those two decisions are what we want to make through prescriptive analytics. And in my group, we are trying to build trustworthy models for decision-making systems. And specifically, like if you ask, what is the definition of trustworthy? Different people have different definitions. Some people may say if you can learn it efficiently, it is maybe more trustworthy. Or if your decision is safe, it is trustworthy. Or you can say your decision is responsible, or your decision is secure, is more robust to those adversarial attacks, it's more trustworthy. Or your decisions can be understood by human, then it's trustworthy. And we see those kind of different dimensions in trustworthy model in my group. And today in this talk, I would mostly focusing on this part, the responsible part. So by defining responsible, we're saying like how can the machine learning models or reinforcement learning models have this self-awareness, specifically with the technique called uncertainty quantification, right? The self-awareness of the decision making in the real world is pretty critical, actually. Say in autonomous driving vehicles, we do not trust the machine learning models all the time. And the machine learning models should make reliable predictions. And therefore, those reliable definition is mapping to a certain level of self-awareness. Like we want the machine learning model not only just give us predictions, we also want them to give us certain estimation on their uncertainty on those predictions, right? With those kind of uncertainty, it maybe for a human, we can reject a decision made by the machine learning systems, and in case of high uncertainty, right? So this kind of uncertainty is what I'm going to talk about mainly in the system. And if we take a statistic point of view on the uncertainty, still using this example of autonomous driving vehicles, we want our model to predict an output, like this is a steering angle of your autonomous driving vehicle, and this one is an input image. And this is a classical regression problem. Like if you do this model, your model is likely to formulate in this objective function where your goal is to minimize the prediction error on the ground truth steering angle and the predicted ground angle, right? So this is the classical regression objective function. But if you want to equip this regression model with uncertainty, one classical way is to say, we assume our prediction is this Y prediction is sampled from some Gaussian or normal distribution. Like say we have this mu and sigma to decide the variance, like the mu to decide the predicted mean of your steering angle, the sigma to decide how the variance would be. And then with this formulation, like if you assume your predicted Y is sampled from a Gaussian, then you can formulate your objective function this way. Because you have this Gaussian distribution, and you can write the probability density function, and through this loss function here, you can write it in this way. And this is how we get this mu and sigma from the training data. Right? And this sigma squared here, actually has some measurement on the uncertainty already. So this is what we call the data uncertainty. It measures the inherent variance in your data. Say, if your training data is like this, I'm going to learn this model, like the red line here. This is a learned model. I'm going to learn this red line here. It's a visualization of the mu. And for each mu, I'm going to predict a sigma square. And this sigma square captures the inherent noisiness in your training data, right? So this data uncertainty, also people call it aleatoric uncertainty, measures the natural randomness inherent in your data. And it can be induced by your data noise and measurement errors. And also, it cannot be reduced by more training data because your data is already noisy in your training data, right? And there is another source of uncertainty which this kind of model do not capture, which is the epistemic uncertainty, which we call model uncertainty. So think of this way, like previously we were predicting purely on this one, right? This range. This range is where your data, your training data is from. It's within the distribution of your learned model. But what if you are making predictions outside of your distribution? Then even though with the same training data, say different machine learning models could have different lines outside of this distribution, right? So one of your machine learning model could be like this, one could be like this, and one could be like this. And this variance is actually we call the model uncertainty, where when you're predicting outside of your training data, like outside of the training distribution of your data, then you are encountering a lot of like model uncertainty. Also, we call it epistemic uncertainty. And this one can be reduced by more training data. Say, if you have more data here, you would learn more accurate model, and you have lower epistemic uncertainty in those training data, right? And how do we capture this one? Like one direct idea is, say, this one is a mu, right, for different models, predicted mu. And how about like we capture the variance of your predicted mu on this model? And this variance is actually, we call this model uncertainty for this variance here. And unifying those two perspectives, right, we try to predict the y, and the expected value of the sigma square is the data uncertainty. And the variance of your predicted mu is the model uncertainty. And how do we actually like measure, how do we estimate this variance of your predicted mu then? Like I said, different models, like different machine learning model, even though they are trained in the same training data, when they meet outside of when they try to predict outside of the distribution, then they have the variance, right? And then one like intuitive idea is saying, like, how do we do Monte Carlo estimation? Like, if we want to estimate the variance of the mu, how about like we train multiple models and we just calculate their variance of the mu, right? So we train multiple models, and different models can give you different mu's and sigma, and we just calculate the variance of the predicted mu, right? This is a very intuitive and a very straightforward way to predict this variance, estimate this variance. And if you visualize this sigma and mu in those two-dimensional space, x-axis is mu, y-axis is the sigma, the different mu and sigma would like related to those different point here. And you could see like you have those shapes. And with this shape here, you would expect something like this. So if you have a low data uncertainty, your expected sigma square would be very low, right? And if you have low model uncertainty or epistemic uncertainty, your mu is pretty close to 0, right? And the variances could be very small, right? And then if you have high data uncertainty, say this one, you have high expected value of sigma square. This variance is, like, this expected value is very high. And you have small variance on the mu. This means that you have low model uncertainty. And for this case, you have both high data uncertainty and high variance on the mu, so it's high model uncertainty. So something like this really measures like what is the model uncertainty and what is the data uncertainty. And instead of like doing the sampling, so you can see that these sampling methods or ensemble method have a like very straightforward drawback, which is you have more parameters to train, right? So you have multiple models here, or like you have, whenever you're making a prediction, you have multiple inferences time, like you have to do multiple runs on this inference. Since like these models are getting larger and larger, this latency would be very high, right? And then people have been investigating models like methods to get rid of this. Instead of sampling those ensembles, how about we directly learn those distributions. And this is one method they called evidential deep regression, where they directly model this distribution through an evidential prior. So instead of like saying we're learning this mu and sigma, they assume that this mu and sigma has also follow some distribution. They also have certain priors. Like they put the evidential prior here, which is a normal inverse gamma distribution, and they sample those two parameters out of this prior. And all you're going to do is you're going to learn those 4 model parameters for this evidential prior. And you can see that on the right-hand side, this one is an example of a learned evidential prior. And whenever you're going to make a prediction, you're going to sample from this prior. You got different distribution parameters for mu and sigma square. So for here, if you sample from here, you get this distribution. And when you're making a prediction for the y, your likelihood function is going to be like this. And you're going to make predictions and by sampling out of this likelihood function, which is a normal distribution here. Right? So this is very intuitive, and they have this nice shape to capture the mu and sigma square. Okay? And this implementation is also very intuitive, like very simple. So instead of like doing output on mu and sigma, you just output 4 parameters. Those 4 parameters are used as the evidential priors. And then you use this loss function that can optimize those 4 priors and can capture the model uncertainty and the data uncertainty. So if you want to calculate, if you have a well-learned model and you want to calculate the aleatoric uncertainty, just use this function. And if you want to calculate the model uncertainty, you've got to use this function here. And in our recent paper submitted to this year's AAAI, if luckily we're going to see that in the next few weeks, we found out like this vanilla function here has certain drawbacks. Say, if the alpha is really equal to 1, you would really have like high uncertainty on both data uncertainty and model uncertainty. So we prove that when like this alpha is equal to 1, this model here really cannot learn anything. So we propose a new strategy by adding a regularization term to say that if you are encountering those alphas near to 1 and you're facing this high uncertainty area, with this regularization term, you can move into a low uncertainty area by training your model with this data. And this one, like I said, hopefully we're going to see that in next year's AAAI. And we have some certain experimental results. This is a toy example. Say here, this one is, we're using the training data sampled from this distribution, this known function. And this known function is the red dashed line here in this 4 figures. And all the training data are from the range of -4 to +4. And you can see that with the original evidential deep learning models, they are predicting well on the in-distribution data, right? And their uncertainty, the blue range is their estimated uncertainty. Their uncertainty is well capturing the data distribution. But when we encounter outside of the distribution, and then these evidential deep learning models, they are not capturing the ground truth. They are not covering this ground truth. But our model can sort of capturing that. And especially when you are having these high uncertainty areas, they are giving you nonsense, uncertainty estimations. They're covering the whole space, not really helpful. But with our method, it can give you certain good estimations on the uncertainty. This is one on the toy example where we know the ground truth. How about the real-world data set one? So we especially care about the out-of-the-distribution thing because as metacognitive models, we want them to tell us whether you are encountering some examples that you have not seen before. So this one, we are training our models within this data set is called NYU depths. The goal is to predict the depths of these objects in the image. Say if it's redder, then this means it's closer to you. And if it's bluer, then this means it's further to you. So this one is we train it on the NYU depths data. And we test it on different both on this NYU depths data and a data set he had never seen before. It's called Apollo Scape data set. And then this data set, you can see that our models can predict it pretty good, like give you good estimations on the predicted depths. But also, one thing I want to mention, like it can give you this entropy where it measures how certain and uncertain it is for this prediction. You can see that for those out of the distribution data set, we're predicting with a lighter, with basically high uncertainty. So this kind of model basically can captures whether your predicted data, your data samples encounter fit into the model is within the distribution or outside the distribution. And this example just shows that we have larger difference on this in distribution and out of distributions prediction, right? And this one is basically says like you can use evidential deep learning models with improvements, and you can use these models to give you estimations on your uncertainty. And then I'm going to give you certain examples on how do we actually use this uncertainty or these evidential deep learning models in some decision-making tasks. So this one is what we call sensor placements, decision-making. This is a real-world situation where we got this question from the traffic engineers. And they're saying like, now this task becomes, now we have certain like 30 spaces, like on the highway, we have 30 locations that has already installed the sensors. And now we want to install more sensors, but where should we put these sensors then? And then we model this task, and they used to decide by random sampling. Say we have like, there's 170 locations as candidate, we just randomly sample 10 and install the first 10 into this system. And that's what they do. But we propose that, how about like we integrate with some uncertainty estimation. Say, firstly, for those traffic sensing tasks, if you are install the traffic sensors, you're sensing the traffic. How about like we do like graph neural network, firstly, to model the predictions, model the dynamics of the whole network. And this graph neural network can handle those predictions for locations even though you are having no observations. Say the original graph, like if you represent this neural network as a graph, say if your original graph has 2 missing points, like those 2, 7 and 10, they do not have sensors, so we do not know their features. And we only have installed sensors around it, like this one. And how about like we subsampling this graph and into a new graph? And since we know this graph's data, right, so all those kind of data that we know, we can train this data through supervised learning. And this graph neural network can be used to predict the traffics for the nodes in the graph. And then during testing, and you're going to feed in the original graph. And this graph neural network can predict for those unseen nodes like they were encountered in the training space. Right? Basically, this graph neural network can handle these predictions, can give you certain predictions for unseen nodes. And with these predictions, one direct question like they ask us is, how about like why not we just use these locations like with largest prediction errors on uninstalled locations? And we say no, because in this example, in this task, they have like in real world, they already installed 20 sensors. Like during our training phase, we treat 30 as uninstalled, 170 as we treat 30 as installed and 170 as uninstalled, so that we have the ground truth for our prediction. But this ground truth prediction cannot be directly used for decision making because in the real world, this error you do not know. You do not know your prediction error on those uninstalled sensors, right? On uninstalled locations. So we cannot directly use the predicted errors. Then that motivates us to say, how about like since we have the predictions for the unseen location, how about we add some uncertainty quantification to quantify your prediction? And we just select the most uncertain predictions so that this most uncertain predictions can be installed and it can be integrated in the model next round so that you train your model so that you get a better prediction. So this is an example saying like this measurement on the predictions given by the graph neural network, and this uncertainty is pretty high, and say we are going to install those sensors on those high uncertainty area. Right? This one is the uncertainty estimation, this one is the errors. And we're gonna use this uncertainty for the installed sensors. And this is what we do, do the experiments. So we start with 30 sensors, and we gradually increase our installed sensor. And this one is a prediction error on this installed locations. Basically, we're saying if you only have the budget of installing 10 sensors, maybe you should just install it in the highest uncertainty. It's performed definitely better than randomly sampling your locations to be installed. Right? Because it gives you lower errors on the prediction and give you more accurate sensing. Right? This is one application of sensor placements where you use uncertainty to quantify your predictions, and you just add your sensors on those most uncertain predictions. Right? Another application is what we do called sim-to-real transfer. This one is a long-term challenge for policy training, and if you want to apply it to the real world, it's going to be some nightmare you're going to encounter. Say the sim-to-real gap, like when you transferring your policies, training the simulation and transferring in the real world, it's highly likely you're going to face this challenge. Because the main reason is because the simulators, they're not that realistic. The dynamics are not different, or there are some unseen components you cannot model. So that when your model trained in the simulator, it will fail in the real world. And in this example, we're showing that under those 4 scenarios where you have different weathers in your simulator or different vehicles in your simulator, your performance is going to drop dramatically. Those blue lines are these training performance, the lower the better, and these orange lines are the testing performance where you have larger drop on your performance. And how do we use this uncertainty quantification to do sim-to-real transfer? Firstly, we have to rely on the existing sim-to-real transfer models. This one is called grounded action transformation. So this key idea of this grounded action, so this loop is, if you do reinforcement learning, you're going to see this loop very often. Say, this is my policy. I'm interacting with my environment, right? By feeding my actions into the environment, the environment gives me some reward, and I'm getting the next state from this environment as well. And this grounded action transformation is simply just adding 2 models in this loop. The first model is called the forward model. The forward model basically predicts what happened what will be in the next state in the real world. Say, giving you the current state in the simulator and giving you the current action, I'm going to predict if in the real world I'm in this state, I'm doing this action, what it's going to be for the next state. And this inverse model is going to take the output for this next state and stemming from the current state in simulation and with this real-world next state. The goal of this inverse model is predict the next action, predict the action that can lead the simulation from state t to state t plus 1. So you can see that those inverse models sort of induce your simulations more lookalike to the real world through the grounded action. This grounded action feed it into the simulation again, and your model is going to learn purely through simulation, right? And we can see that this this model here is likely to have very high uncertainty to enlarge your performance gap, because if your data is really small in the first round of your exploration, or your forward model have very limited data, then you would have very high uncertainty. So how about we directly add some uncertainty output on this inverse model when you output an action, and when you along with the output, you're going to have an additional output on the uncertainty. And we're going to dynamically change and update your threshold for this uncertainty. If your predicted action or predicted uncertainty is smaller than the threshold, we're going to take this action. If it's larger than the threshold, we're going to use the original action so that your models can explore fully in the environment, right? And we conduct experiments on the sim-to-sim scenario because it's more reproducible. And of course, this is our experiments. This result is lower, the better we perform the best. And of course, since we do this dynamic threshold on the alpha, we also do the experiment saying like the dynamically changing your threshold works definitely better than just using a fixed threshold for your uncertainty. And we also try different kind of uncertainty quantification methods, and this evidential deep learning method performs the best. And there could be like a lot more possible applications, and I'm just gonna like talk a little bit about what we have done before and what's a possible application for uncertainty quantification on those different dimensions. And we have done a lot of like efficient online learning for reinforcement learning, and we also do efficient offline learning for offline reinforcement learning. And uncertainty quantification can be directly used here to say how can we integrate those offline learning model. Like when your offline learning model is uncertain, we should not use that. And how can we do exploration during the online learning phase when we have this uncertainty estimation. We also have like those adversarial attacks where we firstly show that those well-trained reinforcement learning agents are not that robust. Say here in this left-hand side, this is the video open sourced by OpenAI. So their goal here is to train this blue robot to reach its destination, the right line. So it's a well-trained model, and it is open sourced by OpenAI. They believe that it's a good model. And we show that this model is really easy to be attacked. Like say we transfer this model directly into the same environment, but we train our agent here differently to attack this well-trained reinforcement learning model. So you can see that even though it performs well, they believe it performs well, but we can easily attack it by some weird actions. And those uncertainty quantification methods can be directly applied here because we can decide when should we attack it and when should we not attack it if you have a limited budget. Right? And also, like, since we're doing the real-world deployment, we also have the challenges from the data. I do not have the time to discover it, but basically the real-world data, they're noisy, and when you have this noisy data, direct method would be using uncertainty quantification to quantify your data uncertainty so that next round you can add more data. Right? And this is basically summarizing our group's work, and we do real-world data mining and do trustworthy model, and we do a lot of deployments and benchmarking. I've only covered this a little bit part about responsibility on the model, and if you want to discuss more about our research, I'm happy to discuss it. And that's it. Thank you.